We're going to be moving on now to the next unit, which is mostly Chapter 8, but we are going to go back for the 7.3 here, dealing with multivariable linear systems. Our big essential goals in this unit have been, how do I deal with a lot of information coming at me, and how do I organize that so that I can do some sort of process or an approach to solve it. So again, that essential question is, how do I set this up so that I can problem solve through this and create a process? So again, what you'll see here is our objective for 7.3 is to set up the appropriate amount of equations to solve for given unknown variables. Right? What we found is if you have one unknown, you need one equation, right? Linear equations, we can solve for those. If you have two unknowns, we needed a system of two equations, right? So you had two variables, you need two equations. If you have three unknowns, you're going to need three equations, and so on and so forth. Alright, we are going to use this process called row echelon form to solve for the system of equations. Again, we're stepping ourselves up to dealing with a complex amount of data or complex amount of unknowns and figuring out how to solve it. Alright, so here is just a quick recall. We came off an activity today where we kind of worked with, you can do a bunch of different things to a system and still call it the same system. For example, you could switch these rows around, and this one's kind of the more obvious, but you could still call that the same system. I mean, this and this are the same exact thing that you're trying to solve. Alright, another thing that we experimented is that you could take row 1, or this equation 1, and multiply it by -2, and add it to row 2, and make that your new row 2. Okay? And if you were to do that, so I'm going to go ahead, we would have -2x plus 2y equals -2, because I multiplied everything in this equation by -2, and then I could add it to that second equation, and what I would get is these would be gone, 3y equals 3. So you could also claim, I'm going to replace this by adding those two rows together and taking a multiplier to it. I got 3y equals 3 as my new R2 or row 2. This also is the same as these, and that was one of those observations that we were trying to make as a class today. Now what we're moving on to today is we're really going to be looking at three unknowns, so x, y, and z. What we're doing is we're moving on to not just the two-dimensional plane, but the three-dimensional plane. So we're adding another axis, orthogonal or perpendicular to these other ones. Okay, so the idea is we have three unknowns, alright, x, y, z, and so therefore we're going to need three equations. Now we're just going to focus on this. So the solutions will be one of three cases. Well, just like when we had linear equations, or those linear equations, we had only one solution we could expect, and that would have been ordered pair, but now we're going to have an ordered triple, right? Because we have an x, y, and z. We also have a possibility of having many solutions, and of course no solutions, right? So this is one thing in other math books you might hear as a consistent system. Our math book doesn't use this, and this would be inconsistent, okay, if there is no solution. So this is kind of a visual of what we would look at. Here's some more visuals. So here would be a consistent system where you would just have that one ordered pair. Somewhere on that 3D axis, you would have this intersection point of these planes. Alright, instead of just lines that we're working with where there's one intersection point, we're working with entire planes when we're talking these three variable equations. Okay, here's an example of an infinite, if they just so happen to all line up so that they intersect in a line. That would be where our planes would have infinite solutions. This is something that we would call inconsistent. If our planes were all parallel to each other, they never intersected. And then also these ones, where our planes were kind of in a randomness such that they never all three intersected. So the goal in this process of solving multivariable equations is to get what we call a collection of equations. It's a 3-2-1 system. So I'll talk a little bit more about that, But we want to, just like we had it with the two variable equations where you had two variables and then you got it down to one, now we're going to have 1, 2, 3, and then we're going to get it down to 2, and then we're going to get it down to 1. And in that one variable equation we can solve. So we really, this is our ultimate goal, to get a one variable equation so that we can identify one unknown, and then in turn we'll be able to identify them all. Make sure you write your problem right, because if you do not, you're going to do a lot of work for something that wasn't the right problem, right? So we have some offenders of this in the classroom, so make sure, Megan, Jessica, and Jada, that you write the problem down right. Alright, operations that produce equivalent systems. So what we kind of experimented with in class were that we could interchange two equations, right? So for example, in these orange ones, I took this system, and this is the equivalent system where I just took row 1 and I interchanged it with row 3, right? So these things just got swapped. So that's one thing. You haven't changed the system by doing that. You could also multiply one of the equations by a non-zero constant. So for example, I could take row 1 and I could multiply it by negative 2. So I took this row 1 and I multiplied it by negative 2 here, and you can see the result. This is the same as this is the same as this. We haven't changed the system at all. And then finally, we could also add. So I technically took that negative 2 times row 1, and then I added it to row 3 here. So I added those together, and you can see that I would have gotten that negative 5. Added these together, I got the 5y. These would have canceled each other out, and then these got the negative 10. Okay, so that's what I did here. Now again, this system is the same exact system as this. We haven't changed it. How are we using all of this? We need to solve this system of equations, and we're using what we are calling row echelon form, and we'll see exactly what that means, but it's that idea that I'm trying to get a collection of a 3, 2, 1. So let's say that I'm working with this. I see this 1 here, and I really like working with 1 up here, because then what I can go ahead and do is I could take my row 1 and I could multiply it by negative 2 and add it to row 2 to get a new row 2. So when I do that, I will be getting the following: negative 2x minus 2y minus 2z equals negative 12. And then I'm going to add it to my 2x minus y plus z equals 3. When I do that, this is going to knock out, and that's what we're trying to get, right? We're trying to get this to a 3, 2, 1, so I'm going to work on focusing on getting rid of these. So here I'm going to get negative 3y, and take this really slowly because there's a lot of algebra errors that could happen, and it will throw off your final answer. Okay, so this is my new row 2, so I'm going to rewrite my system. We have x plus y plus z equals 6, and then I have negative 3y minus z equals negative 9. And then this one I haven't done anything to, so I'm just going to leave it. Okay, so the next thing, again, I can see, oh man, if only I could get rid of this 3x. So again, I'm going to use that row 1, but this time I'm going to multiply it by negative 3, and I'm going to add it to row 3 to get a new row 3. So I'm going to get, okay, so those cancel out. Unfortunately, I do get another variable here, but that's okay. We'll deal with it. Equals negative 18. Okay, so I got a little scrunched there, but what I will then be able to do is x plus y plus z equals 6, negative 3y minus z equals negative 9, and then this was my new equation that I got for my row 3. It's negative 3y minus 4z equals negative 18. Alright, so then I'm going to see, hey, these are really close. I need to get a 3, a 2, and a 1. So let's look at these. This is just like what we were dealing with in Chapter 7. Well, we are still technically in Chapter 7. But we're trying to get rid of these so that we're down to a one variable. So let's set these up against each other. So I'm just going to take my negative 1 times row 2 and add it to row 3. and then I'm going to get my new row 3, which is going to knock this one off. So I'm going to get 3y plus z equals 9. And then when I put it up against this is just like what we did. Okay, these are gone. I'm going to get negative 3z here, and then negative 9. So here is my new system. This right here is what we call this stair-step pattern, or this collection of my 3, 2, 1 is what we call row echelon form. And so what at this point we can use is back substitution. So here with this one variable equation, we can go ahead and say, well, 3z equals negative 9 could easily be solved for. So z is equal to 3, right? So once we get that, then we can go back to our second equation with two variables, plug in what we know. So we have negative 3y minus, and then I'm going to say 3, right? And then equals negative 9, so I'm going to add 3 to both sides. Negative 3y is equal to negative 6, and then divide by negative 3y is equal to 2. Okay, and then now I can take my known z, my known y, go back to this equation, and solve for my x. So we have plus 2 plus 3 equals 6, so x plus 5 equals 6, and then minus 5, what we got is x equals 1. So our final system is going to be solution is 1, 2, 3. This is my ordered triple. On that coordinate grid, it's kind of hard to visualize. So this, you can kind of see the xy plane laying flat. We would have gone over 1 up 2, right? That's where we would have been at. But now we're up 1, 2, 3, so we're going to kind of raise this up to be right there. So that point, however you want to visualize it, they're kind of hard to visualize, but you can have the combination of these planes intersecting at that 1, 2, 3 point. Alright, let's do another one. I want you to see some different things that can possibly happen in these processes and get used to them. So for this one, I'm actually going to take row 1 and row 2, and I'm going to swap them just because I want to work with a 1 coefficient. So when I do that, I am just going to get this new system right here. So now this sets me up in a good position to get rid of these because I know I want to, because I want to get a 3, 2, and 1. So these have to go. So I'm going to take 2 times my row 1, add it to my row 2 so that I get a new row 2. When I do that, I'm going to get 1y plus z equals 10. So our new system here, I'll write it down here. Our new system is going to, if you want to, you can do 2 steps in ones. I don't highly recommend it, but I'm just going to go ahead and say I'm going to take 3 times row 1 and add it to row 3 to also get a new row 3. Okay, not the best practice here, but just to save room, I'm going to do that. So here we're going to get, so these are gone. I'm going to get 2y plus 2z equals 16, right? So do check your work carefully because again, this is all going to follow down, and if you do an algebra error, it's going to completely change your answer, of course. So now I'm going to say, hey, I'm just focusing on these guys just like I did with my linear equations of 2 variables, because that's what these are. We're going to take negative 2 times row 2 and add it to row 3, because I have that goal of knocking off this 2y here. So we have negative 2y minus 2z equals 10. Oh, nope, negative 20. And then when I add to this, you can see something goofy is about to happen. These knock off, so I have 0 equals, and then negative 4. So this is one of those cases just like before. If you ever get this untrue statement, our result is going to be no solution. Alright, something's going on here where all 3 of these will not mesh, so we're looking at something like either this or like this. Alright, and one final one here. This one's a little bit strange. This is also not in your homework, but you want to be watching out for this. So here we're going to be taking, I already have my 1 up here, which is nice to work with, so I'm going to take negative 2 times row 1, and I'm going to add it to my row 2 to get a new row 2. So here is that. Alright, now I'm going to go ahead and take my row 1 again, and this time focus on that third equation that I want to get rid of the x term in. So, alright, and you can see another goofy thing is about to happen. So if I did take negative 1 times my row 2, added it to my row 3 to get a new row 3, you're going to see that these are going to cancel each other out, right? So boom, boom, 0 equals 0. So this is a true statement. There are infinite solutions. Alright, but now here's the deal. Infinite solutions. This is where we're going to go ahead and say that, hey, I still can get a coordinate pair here. So it's where I can't really put these up against each other. So now I have this two-variable equation that equals another. So this is where I'm going to say, well, let's solve for one of my variables. I'm going to go ahead and solve for my y. So if you solve for your y, I'm just going to set this up down here. I'm going to add 3z to both sides. So negative 3y equals 3z, and then when I divide by negative 3, we get y equals negative z. So here is where I'm going to say, well then y can really be equal to any kind of value. Let's say that we just are going to use a for z. So plug in anything for z, then y would be equal to the negative of it. So in my ordered pair, I'm going to let z be anything, okay? And then therefore y is going to be negative a, okay, that negative anything. And then what I can do is I can now solve for my x at this point with that back substitution. So x plus, and then y, which we said would be that anything that I put in but negated, plus 2 times a, right, equals 1. So now I'm going to simplify x plus, and then 1a, when we combine those, equals 1. And then x equals, when I subtract off 1a, 1 minus 1a. Okay, so x in this case is 1 minus 1a. What I want you to see is you could go ahead and play around with that, and let's say that we let this be a equals 1. Okay, so in other words then we would have 1 minus 1 times 1, so 0, comma, then negative 1, comma, 1. If we were to plug that into all three of these equations, it would work. Okay, so let's say that I plugged in 0, negative 1, 1. It's going to be negative 1 plus 1 times 2 is going to get me 1 here. Okay, so that worked. Here is 0, so it's going to wipe that out. Negative 1, so it's going to be positive 1. And then plus 1, so there's my 2. And then here as well, 0, that knocks that out. And then I'm going to have negative 1, and then a 1 here. That's going to get me 4. So these, a could work with that. If I use 2, it would also work, okay? So I could also go through here and say that this was 2 times 2, and then all of this times 2. These would also work, right? Because they're just multiples of whatever I have there. So the idea is, if you come to this point where you can't go any further, you have a true statement, or you just have a two-variable equation and you can't go any further, which you will, the idea is, well, solve for one of the variables and then back sub just like you would have. Alright, so there is your practice set. Good luck.